Hi, it's Mrs. Weethy back for Unit 2, Video Lesson Number 2, The Discovery of the Electron. Let's first define the atom since we now know that the atom does exist. The atom is the smallest unit of an element of matter that retains all the properties of that individual element. Dalton's model of the atom is very simply described as a solid, indestructible, indivisible sphere. And we can draw a picture of it, and it would just look like that red sphere that we have there on the slide. Now, once Dalton established the existence of the atom, new questions were asked, and this happens all the time in science. Once something is established, then we ask more questions, and that leads to more investigation and more theories and more laws and new discoveries always taking place in science. So some of the questions that scientists asked was, what is an atom really like? Is the composition of the atom uniform throughout? Is the atom made up of smaller particles? We can probably think of more questions like what contributes to the chemical properties of the atoms. So research began to find a connection between matter and energy and wondered how electricity would behave in the absence of matter. We had the cathode ray tube around that time. It was invented by Sir William Crookes. And here's a diagram of the cathode ray tube. And I would like you to draw the diagram in your chill. So it was a glass tube, kind of like an oblong shaped tube. And it was actually sealed off. It was an enclosed tube. And we had this little piece coming off that was attached to a vacuum pump. So all of the air was pumped out, while gas at very low pressure was pumped in. The gas was an inert gas, so it didn't react with anything. On one end we had a metal plate, which was called the cathode, and on the other end we had another metal plate, which was called the anode. Now, a little wire extended out from those and was attached to a generator or some source of electricity. So the anode had a positive charge because it was hooked up to the positive end of the battery or a generator, and the cathode had a negative charge. And so the next couple experiments that we talk about uses this cathode ray tube, otherwise known as a CRT. Now, what Crookes observed that when an electrical current was applied, a beam of light was produced originating at the cathode and moving towards the anode. And this ray of light was called the cathode ray. And you can see this here. This is a Crookes tube, also called a cathode ray tube. And so here we have the cathode end, and here we would have the anode end. And you see this green light that is produced here. It's just a straight beam of light. And so what he hypothesized is that that ray was composed of negatively charged particles because they moved from the negative end to the positive end. Now, this was a hypothesis, and he didn't really act upon this. We had an English physicist that acted upon that hypothesis. His name was J.J. Thomson, and that's J.J. up there in the corner, and he performed several experiments using the cathode ray tube. One of the first things that he did is he put a paddle wheel inside of the CRT. Now keep in mind what the hypothesis was, is that the cathode ray was made up of negatively charged particles. So he put this paddle wheel, as we see right here, inside of the CRT. And what he observed is when he flipped the switch, basically, applied the electricity, and produced the cathode ray, the paddle wheel spun. Now, if you take a flashlight, you take any beam of light and you shine it on a paddle wheel, that paddle wheel is not going to spin. But in this case, the paddle wheel did. It spun. And the conclusion that J.J. Thomson made was something with mass had to move the paddle wheel, had to hit that paddle wheel in order for it to spin. So it's phenomenal observation and conclusion at that time. The second thing that he did then is now he put an object in the path of the cathode ray. And when he applied the electrical current, he noticed that the cathode ray cast a shadow. So here you have the cathode ray is coming from this end. Here you have the object, and on the other end on a screen you had a shadow of that object. And so the conclusion was made that the ray had to consist of particles moving in a straight line in order to cast the shadow. So these particles moving in a straight line, okay, and they're not bouncing off of that that object. They're just moving in a straight line and then hitting the fluorescent screen on the other side. And so where that shadow was, no particles were hitting that fluorescent screen, and that's what's making the shadow. So it had to be particles moving in a straight line that were producing that. So that basically confirmed that the cathode ray was made up of particles. Now what about the charge? So Crookes hypothesized that that cathode ray was made up of a negatively charged particle. So here's what J.J. Thomson did. He used a magnet to determine the charge. The first test was that he placed the negative end of a magnet near the cathode ray. Well, he said that hypothesized the cathode ray was made up of negative charge. Well, what do you know happens when you put negative charge near negative charge? Like charges are going to do what? That's right, they're going to repel. And so this was the observation that J.J. Thomson observed. When you put a negative charge near the cathode ray, that cathode ray is going to deflect away from the magnet, suggesting that that ray had to be made up of negative particles. The second test then, he just flipped the magnet over and put the positive end near the cathode ray, and if that cathode ray was negative, then the cathode ray would be attracted to the positive end. And so this is what was observed. The cathode ray then bent towards the magnet, was being attracted to the magnet. And so the overall conclusion then was that the cathode ray is composed of very small negatively charged particles that J.J. Thomson dubbed the electrons. And that was how the electrons were discovered. Pretty cool, wasn't it? In his further experimentation, then J.J. Thomson determined that the mass of the electron was much less than the mass of a hydrogen atom, hydrogen being the lightest element that was known at the time and is still known. Thus, the mass of the electron is considered to be negligible. It means that it's really too small to count towards the mass of the atom. Even though we know that atoms have mass, it's not the electron that is giving the mass to the atom. So even though his work was really hard to accept, because up to this point we thought that atoms were indestructible and indivisible, and now we're showing that yes, there are parts to the atom. We have this really, really small particle whose mass really is too small to count, has a negative charge. His ideas were revolutionary, but correct, because they were tested over and over by other scientists, and he won the Nobel Prize in 1906. Now, the next significant development was the oil drop experiment that was done by Robert Millikan. Now, the interesting thing about Robert Millikan, as we go through the history of the atomic structure, we'll see that most of the scientists were German scientists, English scientists. Robert Millikan was the only American scientist from the University of Harvard that was in that quest to find the atomic structure. He, in the early 1910s, or the early 1900s, confirmed the charge of the electron and also determined its mass. And he did this through the oil drop experiment. He used the known charge to mass ratio and found the mass of the electron to be 9.1 times 10 to the minus 28. That is so small, or roughly 1/2000th the mass of a hydrogen atom. So like 2,000 times smaller than the mass of a hydrogen atom. That is very, very significantly smaller. So that's why we say the mass of the electron is negligible. This ultimately led to the second model of the atom, which was called Thomson's plum pudding model, and kind of looked like this. You have a sphere, a positive charge, and within that sphere you have embedded electrons to neutralize that positive charge, because we know that all atoms were electrically neutral. So positive sphere with embedded electrons. Now, why was it called plum pudding model? Because Thomson's favorite dessert was plum pudding, and it would remind you of having bread pudding with raisins in it or little plums. And so he said his model of the atom reminded him of his favorite dessert, and that's how the name Thomson's plum pudding model came about. So with every new discovery, new questions came about, and the search was on to answer these questions and to make new discoveries. The big question, or I should say a few questions, if there are negative particles and the charge of an atom is neutral, then could there be a positive particle? In addition, if the mass of an electron is negligible, then what contributes to the mass of the atom? And then finally, we still don't know what contributes to the chemical properties of the atom. So these were questions that scientists at that time in history wanted to answer. That, my friends, is the end of lesson 2 on the discovery of the electron and the second model of the atom. Until video lesson 3, goodbye for now. This is Mrs. Wheathy.